stock number, and then you want to compute it. Yeah, they also like to read the papers on eager or new papers or like. I'm looking forward to another great presentation. Thank you very much.
Yeah, thank you for the invitation. The mic seems to work. Yeah, it's always a pleasure to come back. Like for Singapore, the food is great here. So that was one of the main reasons back then. No, it was also nice university and nice experience. Today I would like to talk about quantum optimization, and particularly quantum optimization in what we call the era of quantum utility. And I will introduce what we mean by that. And you may think, okay, yet another term. We're not talking about quantum advantage, we're talking about quantum utility, which is a step in between. And this is the outline. So first I'd like to talk a bit about quantum advantage in optimization, what to expect actually, and from a complexity theory perspective. I think quantum optimization is, from this perspective, probably one of the most misunderstood topics, and I'll get back to that. Then I want to introduce quantum utility, the concept of error mitigation in the context of quantum optimization, and then I show some results that we achieved end of last year on real hardware, and give some outlook. All right. Particularly the first part is mostly based on this paper. This is something we wrote also by end of last year, and it's really like it's a complete overview of the topic of quantum optimization, and discusses where we stand, what we know, what we don't know, and what are good directions to move forward. All right, so this is a statement I frequently hear, that you might have heard as well, that in quantum, particularly in combinatorial optimization, we should not expect more than a quadratic speedup. This is kind of the one extreme. You might also have heard that a quantum computer solves everything in parallel and you get the optimal solution immediately. That's on the other end of the spectrum. And I want to shed some light here into this from a complexity theoretical perspective. And what I'd like to discuss is not what we can say, but what we cannot rule out, which is an important difference. Okay, so let's get back to this statement. This statement refers to difficult problems, so problems that are NP-hard, where the runtime of provably exact classical algorithms scales exponentially. What this means is, suppose we have a runtime that scales as 2 to the n classically, then what this statement means is that with the quantum computer, the best you can achieve is 2 to the n half. Okay. If this would be the end of the story, then neither classical nor quantum optimization would make much sense. Because this is exponential, this is all scaling too bad. If you want to solve any practically relevant problem with these runtimes, you're doomed. I think this is important to understand that this statement, actually, if you refer to that, then classical optimization also is not very interesting. Luckily, the situation is not that simple, it's much more subtle, and I want to introduce that a little bit and discuss this for different cases. Okay, so we have these two problem classes, NP, which stands for non-deterministic polynomial time, and P, which stands for polynomial time. So these are the ones that you can solve efficiently classically, those are the ones that usually scale exponentially classically. And here are some examples, max cut is NP, TSP, and shortest path, for example, is P. But already on that level, it's not that easy, because NP actually divides into NP complete. Those are the most difficult ones, and NP intermediate. We already heard about factoring. And there's another one, graph isomorphism, for example. Now, if we look at that, what does this mean from a possible quantum advantage perspective? So, if we talk about NP complete problems, then indeed it's widely believed that we have at most a quadratic speedup. Already, if you go to NP intermediate, the speedup can be exponential, as we know for Shor's algorithm. I mean, there is an example, there's a complete example, and it can be exponential. If we talk about P, then the situation is a little bit more subtle. In principle, it can be exponential, however, under certain conditions. First, you need a compact, let's say, functional representation of your problem. And you need to have a way to read out the result efficiently. What do I mean by that? Suppose your problem is specified by a matrix, and you're interested in a vector. Then loading this problem is as complex as like writing a matrix. There's no way around that. That means this is kind of a lower bound on the runtime of an algorithm. So if the quantum algorithm is supposed to give you a logarithmic runtime, you can't even load your problem. So there are just some limits to that. However, if you have a functional description of your problem, then you might load this function, and that's more efficient. So there might be exponential speedups, but under certain circumstances. And one has to be a bit careful because we now kind of simplify to a special subset of problems, the ones that we can describe by a function. And of course, classical algorithms may also be able to leverage that function and structure. This, you might have heard about this. This has happened to algorithms for recommender systems. There used to be quantum algorithms with an exponential speedup, but then somebody kind of dequantized that, and under this computational model could show that you can also get a polynomial algorithm there, classically. All right. So this is if we look at exact algorithms. So algorithms that give you the provably exact solution, globally optimal solution. This is a very strong statement, and in practice you really don't care. So what is it if we talk about approximations? Let's first quickly introduce approximations. Approximations are algorithms with an a priori performance guarantee. So if I know up front that, for example, for MaxCut, there's a Gunnar-Williamson approximation, this has a guarantee that you achieve an 87.8% optimal solution. It's a lower bound. And this always holds. In this case, there's also a so-called inapproximability bound. So we know that if you want to approximate MaxCut better than this 87.8%, then it becomes NP hard. So there's kind of a phase transition. Below this threshold, we know efficient classical algorithms. Above this threshold, it suddenly becomes NP hard. There's another example, metric TSP. Here the situation is different. It's a minimization problem. That's why we have these bounds larger than 100%. The lower bound, the inapproximability bound, is 101.3%. So we just know that approximating better than that definitely becomes NP hard. But the best approximation that we know achieves only 150%. So there's quite a gap in between. The other algorithms, like the polynomial time approximation schemes, in these cases, for every target approximation ratio, epsilon, you have a polynomial time algorithm, but the smaller you make this epsilon, the larger the degree of this polynomial usually. So you can have it, but it still becomes, of course, more and more expensive. Now, in terms of quantum advantage, for this approximable or approximation algorithms, in principle, we can have an arbitrary speed up in the runtime of these things. So nothing rules that out. And in cases where the approximation ratio doesn't achieve the inapproximability bound, we can also have quantum approximations with a better approximation ratio. That would not rule out classical algorithms that maybe achieve that later on. But for the time being, this is something there's still room for improvement. It's not ruled out by complexity theory. It's something it's worth looking for. Now, this is all for approximations where we have a provable a priori performance guarantee. And again, in practice, I want a good solution. I mean, I don't care too much about a performance guarantee. So one may ask, what about heuristics? And let's quickly introduce heuristics. So heuristics are algorithms without any a priori performance guarantee. They usually work well for many, but not for all problem instances that you may be interested in. And now if we look at classical optimization algorithms, actually most of them are heuristics. Like in practice, in reality, most of the algorithms don't have any guarantee. Think about simulated annealing, taboo search, all these meta heuristics. They usually work well, but there are instances where they just don't work. And you don't know upfront. It's just like we tried it many times, it worked, we're happy. The statement I started with the quadratic speedup, this does not apply here, right? This really just applies to this most rigorous statement or setting where you want the provably exact solution. Here I have two examples. So for example, there's the Burroughs TSP. It's a Turing assessment problem with 1.9 million nodes. If you think about this from an exponential runtime perspective, this shouldn't be possible. But we can solve this to up to 0.00471 optimality. Now, in contrast to approximations, this is not an a priori performance guarantee, it's a posteriori performance bound. So it's like by lower bounds, meaning lower bounds, upper bounds, afterwards you know, okay, it's that much away from the optimal. There are other examples, hard examples. Here are just a few cases: market share, low autocorrelated binary sequences, quadratic assignment problems. There are more, and those are problems where we know problem instances with only 100 binary variables that are really difficult classically. So this is like on the other end of the spectrum. Small problems, very difficult. Not all of them practically relevant, but they're good cases to study because classical algorithms just don't work very well. Usually, what characterizes these problems is that you need to change a lot of variables altogether to, for example, move from one feasible solution to the next feasible solution. So with local changes of your solution, you will not get anywhere. You really need to kind of global changes. All right. So examples of quantum heuristics are quantum approximate optimization algorithm, QARA, we've heard that before, all the variants, one starting QARA or other variational algorithms, those are all heuristics. And in principle, they can have significant speedups for some problems. Not for all, this is pretty sure this is ruled out, but for some problems this might be possible. It's a bit difficult to talk about a quadratic speedup here because it's on an instance. So this asymptotic scaling does not make too much sense here. It's really just we need to just show that for some problems it works better. So it's really about demonstrating this. What's quite interesting for max cut on 3 regular graphs, so max cut on a special set of graphs, this is still NP-hard, but QARA is actually a provable approximation with a certain approximation guarantee, like around 70% depending on the target is. And we'll get back to that later. It's not achieving the best classical bound, but it's kind of a quantum approximation. So it comes with a a priori performance guarantee. All right, now I'd like to take a step back a little bit and talk about errors, error mitigation, and some of last year's results that we then will use also to approach quantum optimization from a more practical perspective. So this was now the first part, really what can we expect in terms of quantum advantaging optimization. And it's not all solutions at the same time, it's not only quadratic speedups, it's really like a lot of facets in between. It's quite subtle to really understand what applies in your case that you may want to look at. Okay, so you know in quantum computation we have to deal with errors. This is a quantum circuit with 4 qubits. We apply these single qubit gates, 2 qubit gates, we measure at the end, and everything in this circuit can go wrong. The gates might not do what they're supposed to, qubits may drift, you've seen the state of the blocks here, maybe they just drift. They might decay to the ground state, and we might get errors when reading them out. There are different strategies to deal with that. The first one is error correction. In error correction, you use multiple physical qubits to build one logical qubit. You fix errors during the computation, and you then read out this logical qubit. The alternative is error mitigation. In error mitigation, you try to learn the noise or characterize the noise somehow, and then you run many noisy simulations or noisy circuits, and because you know the noise, you can combine the results in a statistical way such that the noise is cancelled out and you get a noise-free result. How do they compare? So there's some limitation on the gate set for error correction. It's a universal gate set, but you can't do arbitrary operations, you can't do arbitrary unitary matrices on the block sphere, but only a subset that if combined, you can represent everything, but it might be a bit more expensive. With error mitigation, we can do essentially every single qubit gate, for example. Then the qubit overhead for error correction is relatively large because you have to have this redundancy. You have to have many physical qubits for one logical qubit. For error mitigation, it's none. Circuit output. This mainly corresponds to can you only look at expectation values, so averages over samples, or can you also do samples from a quantum circuit? With error correction, you can do both. With error mitigation, you usually can only do expectation values. So because we combine noisy results, we know that on average the result makes sense. We don't know that every individual sample makes sense. And Here the sampling overhead for error correction is essentially none. For error mitigation is large, and overall the scaling will be efficient, polynomial for error correction, and exponential for error mitigation. So here you may wonder why looking at error mitigation if it's exponential. And we illustrate this here with this chart. Think of the x-axis as kind of the problem complexity, the size of the problem, and the y-axis as the simulation time, the runtime of the algorithm. Classically, this is exponential for these cases. With error mitigation, it's also exponential, but if we get the noise in the device small enough, the growth rate will be smaller than for the classical algorithms. So there's a regime where error mitigation is more efficient, and then error correction is polynomial, but as this overhead, we first have to get into this regime. And at the moment, we're somewhere here, I'll get back to that point. And of course, we want to get to this regime where with error mitigation, we can already achieve an advantage. And then there will be the transition. It's not like a fixed point in time, it's a smooth transition. We can even combine these different techniques. All right, this is actually a recent publication from colleagues in Yorktown, and it's a paper that Frank already mentioned before. So this overhead of building logic in qubits through error correction, this can be quite significant. And previously estimates were between 500 to 1,000 physical qubits per logical qubit. And this very recently has been pushed down quite a lot to, that's 24 to be precise. I just wanted to have more nicer numbers here. So it's like an order of magnitude reduction in the qubit overhead. And this is quite a breakthrough that we made it on the Nature cover. Regarding error mitigation, there are two main schemes that we are looking into. It's probabilistic error cancellation. There you characterize the noise, you run your circuits in parallel, you combine them such that you know an average, you will get a noise-free value of an observable, of an expectation value. In zero noise extrapolation, what you do is you amplify your noise, and there are different ways to do that. And if you run the same experiment with different noise levels, you can extrapolate to the zero noise limit. So this is the natural hardware noise, you amplify that, and then you extrapolate down to the zero noise limit. These are the two main ideas. And mid of last year, we published this paper on the evidence for the utility of quantum computing before fault tolerance. So this used these error mitigation schemes to run circuits that are on 127 qubits and that are way beyond everything you can do exactly with classical simulation. And we could show that you can produce accurate expectation values here in this regime. Some of you may remember that. Okay, let me quickly go back to that. So what we did is essentially the 127 qubit device, and it's a circuit that does it's a simulation of a, let's say, artificial physical system. It's been simplified such that we can demonstrate it and implement it, and then it's simulating the time evolution of this system. And it's a parameterized system, it has some parameters we can play with, and then there's some observable we're interested in. So this is the parameter we play with. This is the value of an observable that we measure of this system. I think it's the average magnetization of the whole device and of the whole spin system. And then we can track that. And in blue, you have the values, the error mitigated values from the quantum computer, and here in purple and red, you have values from tensor network simulations, from classical approximation schemes. You see there's quite a deviation. And because we also ran other experiments where we knew the exact results, we're pretty sure that the quantum computer actually leads to the right solution. Because now we are in a tricky situation because we don't know the result. The validation is suddenly not that easy anymore because we want to run something that you cannot run classically. So here there was a series of experiments building up in complexity, where we already before saw that the classical approaches deviate, while the quantum approach really showed the right result. Now, some of you may remember that I was standing here and was showing more or less the same already last year. I want to give you a little bit of history here. So the paper was published on June 14. 12 days later, I presented here at the SummerSOC. Probably was the same slide. 2 days later, there was the first paper showing that there are new classical algorithms that actually could approximate these results as well. Luckily, I was presenting before that, otherwise I would have to adjust all my slides. Another day later, there was a second paper showing yet another approach, how to simulate this possibly. On the same day, there was a third paper, and since then there are a couple more. So this similar to breaking the crypto algorithms that we mentioned earlier, this triggered a lot of research how to do that and how to approximate them. Now, there's one very important point here. So this is the different results. In blue, we have again the quantum results, and then these are from all the other papers, some of the other papers, what they predict. And it's quite interesting to see that there's a fluctuation of about 20%, up to 20% between all these classical approaches, and none of them are exact. All of them are heuristics. The only one that has like a solid theory why it should give the right result is actually the quantum computer. So in a way, the quantum computer now validates the results of the classical heuristics. And this is quite a change in paradigm where we are today and what we are doing today. And this is kind of also one aspect of what we call quantum utility. All right. This is another way to look at what this paper did. In 2017, these were the circuits that we could run reliably. And now in 2023, this is the circuit we can run. So it's 127 qubits and almost 3,002 qubit gates with a depth of 60, I think, if you sum them all up. So this is quite a development where we really go from these toy problems to something that's beyond what we can exactly simulate. This also led to quite a disruption in the field. So what you see here is the average number of qubits reported in archive papers over time. And that, if you extrapolate that, it would have taken a long time until we get to anything interesting. But here, when we put this 100 plus qubit devices online, this really led to a jump. So these are not the averages, but these are individual publications, but there's really now like 10, 20, and counting papers that really demonstrate in this 100 plus qubit regime that you cannot exactly simulate anymore. So this is a quite nice development. Okay, talking about development, I'd also like to bring up our development roadmap. We update this usually once a year. This is from November, December. There was a quite significant change compared to what I showed last year. What you see here at the bottom is the hardware development. So we have here the 127 qubit devices. Here we move to a new technology, 133 qubits, 156. But what's important here is the scaling will not be only with the number of qubits on a chip. The scaling will be now also using a modular approach. So here we do kind of classical parallelization. Think about multiple QPUs that can communicate classically during the runtime. So during the execution of a circuit, you can measure on the one QPU and you can apply an operation based on the measurement result on the other QPU. This has interesting applications in measurement-based quantum computing, you can do some operations more efficiently by that way, and also classically create entanglement circuit cutting protocols, make profit from that in certain cases. Now, moving forward here, you see here these couplers. These are now couplers that connect qubits from different chips, not with classical communication, but really with a quantum link. So it's really quantum information that's shared here. And you see this is moving on here more and more, and the goal is then to achieve really error-corrected systems by 2029. So what these numbers here mean, it's the number of gates that we think we can run on these devices. So this is quite indicative of what we expect we will be able to do with them in practice. So I think this is also quite nice as information as a user. Then here you see the sudden jump from 15,000 to 100 million. And here the qubits, these 200 qubits, this is now error-corrected qubits. So this is referring to this error-correction paper that I mentioned before. And the idea is really to scale with this modularity. So here, if you think about 24 qubits per logical qubit, then with about 5,000 physical qubits, you would be able to get these 200 qubits. And here, with this, we are at around 1,000 qubits, so you can imagine if you scale this a bit further, we'll get there. And then, later next decade, we think that we can add another order of magnitude here in the gates and the qubits and push this further. If we relate this to the numbers that you have shown for Shor's algorithm, somewhere here. All right, so this is the development roadmap. There are a couple of more things on top, like developments in the middleware, tools for serverless deployment, resource management, circuit knitting, orchestration. This will also come over time, and then libraries of functions, of mappings, and tools to use that. What came on top of that is the innovation roadmap. This is not necessarily making it into products or something we make available, but it's necessary innovations that we work on to implement these things that I showed on the other side. And this is, for example, these different types of couplers. This is kind of near-term or near-range couplers, longer-range couplers, and so on, how this will up. Error-correcting decoders and all these things that are necessary to make the upper part work. So we splitted this in two. Before that, we only had kind of the upper part, but we want to be transparent about this lower part, but this will not make it into a product. So this is not necessarily things that will be available. Okay. Also last year, we showed the IBM Quantum System 2. This is an animation of how it looks like. And I talked about this modularity, and how this looks like from the top is actually like that. So it's like this hexagon shape with the different classical control racks or also classical compute racks. So this might be actually a quantum NHPC system. And it's built in a way such that you can really plug it together. So it's really modular and you can grow it to the needs that you have towards a larger system. And so with that, we have now entered this era of quantum utility, and of course a good question is now what are we doing with this now? This is what I want to talk now a little bit about in the second part, with the from an optimization point of view. This is not an animation, this is a picture. So this stands in your our research report. So back to quantum utility. I want to quickly define again what quantum utility means. First it means we can run circuits of a size that's not simulable anymore classically and get reasonable outcomes. Second, what it means, and I think this is very important, quantum utility means we can use a quantum computer as a tool to advance science. That can be by testing new algorithmic ideas, for example. It does not mean that we achieve a quantum advantage, but it means that we achieve an improvement, a development that otherwise would not be possible. I wrote here trial and error versus pen and paper. If you think about how classical machine learning has been developed or is being developed, that's not by we first work out a theoretical idea and then we try it. It's by we have an idea and we try it, and afterwards we try to understand it. And quantum computing, this was not really possible. We could do small-scale simulations, but not at scales that are really interesting, that are really difficult classically, where you really may see how this exponential scaling kicks in and leads to different results. So we were mostly limited to pen and paper research in terms of quantum algorithm development. And this now changes, because now we have these devices at a scale where we can really try ideas at non-trivial problem size. And so we really have this trial and error to augment pen and paper. And I think this is really a new era in algorithmic development. And it's a very important step to accelerate towards practically relevant quantum advantage. All right, so let's move to optimization. For simplicity, we look at QUBOs, so quadratic high-constraint binary optimization problems. We have just binary variables, we have no constraints, and we want to minimize this quadratic term. This can be mapped to a ground state problem where you look at for the ground state of an Ising Hamiltonian. I just noted this down here. We don't need to go through that in detail. But in the end, what we're looking for is minimizing an expectation value, and we want the state that minimizes that, and that can be translated back to the solution of the optimization problem. The usual algorithms today are variational algorithms, where you have a quantum circuit that has certain parameters. You measure the expectation value I just mentioned. You use this as a loss function and classically update these parameters of the circuit. You go up, and then you run the quantum computer with the new parameters again and iterate until you converge. The different variants essentially just tell you how you choose the circuit, which for today is not so important. And there are variants that add some more classical logic around that, how you do the optimization and so on. But all following more or less this concept that you have this parametric circuit, you do your update loop, and in the end, you sample to get a good solution. So it's important that there are two things. It's the expectation value for the training loop to find the parameters, but you also need to sample from your final state, because otherwise you know how good you could be, but you don't know how. Right? If you only know the objective value but not the solution, that is sometimes interesting, but usually to implement this action, you need to know the solution as well. So that's why you need to do expectation values and samples. The problem is that this error mitigation only applies for the expectation values. So I might get a good objective value, but I don't necessarily know how to get good samples. And another point, if you want to achieve the quantum advantage, you of course need to do something that a classical computer cannot do. Expectation values are significantly easier to compute classically than samples. That's because usually they only affect a few qubits, usually they are local, and so there's a lot of things you can actually throw away of your circuit, while samples always take the global correlation of all qubits. So this makes it significantly more difficult to error mitigate. However, this whole theory usually comes more from the quantum mechanics, material science, quantum chemistry perspective, where it's really important that this is the exact expectation value, or that the samples come from the exact distribution. Here we can relax that quite a bit in the context of quantum optimization. So let's take this QA example. What we need to do is first find good parameters, train the circuit, and second, sample good bit strings for the solutions. We really don't care whether this is an expectation value, whether this is an unbiased estimator or whatnot. What we want is that minimizing this loss function leads us to a state with high probability of good solutions. And then sampling the bit string, we don't care whether this is the correct probability distribution. We want that it's a probability distribution that has a high probability of good solutions.
Stefan, the first point, the objective function still has to be problem specific, right?
Yes, okay, yeah. But it's not, it doesn't have to be exactly this expectation value that corresponds to some energy and so on. It can be, and I show an example.
Okay.
All right. Before I can now connect error mitigation and quantum optimization, we need to introduce one additional concept. This is called layer fidelity. The layer fidelity is a metric to measure the quality of a noisy quantum computer. And think about this very simple quantum circuit. You have 10 qubits. You have here this layer of 2 qubit gates, and you have another layer of 2 qubit gates. What we can do is now we split this. The splitting is not, there's some ambiguity in how you split, but usually it's clear which one you want, because you want to minimize the depth and the number of layers, so you can forget this lower part. So you have these two layers, and then for each of these layers we have an efficient protocol to estimate the fidelity. And the fidelity is essentially just, you can interpret this as the probability of no error happening when you execute that. And if you can compute this for this layer and for this layer, and the circuit you want to run is 2 times both layers, and you can just multiply the fidelity to get the overall fidelity. And we can do this for a whole circuit and estimate this fidelity of a circuit. So for a whole circuit, we can estimate the probability that no error happens there. And we can do this efficiently if the number of layers is not too large. So we wouldn't like to do this one, but we would use this coloring. And for those of you who are familiar with probabilistic error cancellation, this layer fidelity has a very close relationship to the sampling overhead of this error mitigation scheme. So the sampling overhead is usually denoted by gamma squared, and this gamma is 1 over the layer fidelity squared. So the sampling overhead of error mitigation is actually then 1 over the layer fidelity to the 4. if the layer fidelity would be 10%, then this translates to 10 to the 4 as a sampling overhead for error mitigation. If you are interested in expectation values, so let's just assume we have a circuit and we can compute this layer fidelity as the probability of nothing going wrong. Okay. Now, suppose I give you a quantum circuit and I promise you if you can execute that in a noise-free way, it has a high probability of giving you a good solution for an optimization problem. And since we sample bit strings, we have to first translate them into objective values by applying our objective function. And then suppose the green probability distribution describes the probability distribution of the noise-free case. And this is what you would like to do. Now, suppose you have a noisy quantum computer with a layer fidelity LF, and for this circuit, and this is the only thing you do. So you run this quantum circuit, I promise you it's a good one, on your noisy device. What you get is a different distribution, the red one. And since the green one is good, it's usually leading to smaller, better values than the red one. Now, what we could show is that the probability of the red distribution, or for example for the red distribution, is lower bounded by the green one times the layer fidelity. What this means now is that with 1 over layer fidelity more samples, we can kind of recover the probability of the noise-free circuit. So if again the layer fidelity would be 10%, then with 10 times more samples, I have a guarantee to sample the good solutions at least as often as in the noise-free case. So this gives us a very clear indication of the sampling overhead of running running good circuits on noisy hardware. And if you compare this again to the error mitigation for expectation values, it's now 1 over layer fidelity versus 1 over layer fidelity to the 4. So if you stay with this 10%, it's 10 versus 10 to the 4. Now we come to alternative loss functions. Suppose now we have these samples xi or xi from this noisy state. And we now added the noise-free expectation value, which is usually the loss function to minimize. Then what we use is the conditional value at risk. And the conditional value at risk for level alpha is just like, let's say alpha is again 10%, we take the best 10% of the samples, and instead of averaging over all of them, we just average over the best 10%. And what we then could show is that if you choose this alpha equal to the layer fidelity, then this conditional value at risk of these noisy samples suddenly becomes a provable lower bound on the noise-free expectation value, with a nice property that if the noise-free state would be the optimal solution, then actually we don't have just lower, but we have equality. And if the C bar is equal to the ground state energy, to the best solution, then we know that we have at least a layer fidelity probability of sampling the global optimum solution. So this is now an alternative loss function that has very nice theoretical properties and where we have some guarantees of if that behaves in a certain way, we have a probability of finding the optimal solution.
The 10% that you mentioned, is that only an example? Is it?
No, they are made up. I have an example with a complete number. They are unfortunately a little bit smaller. All right, and this is now in contrast to the expectation value. It does amplify the variance, so we need more shots, but only 1 over layer fidelity more shots to have like a loss function with a certain error, like just statistical fluctuation compared to the expectation value. And this conditional value at risk, this is something we proposed already in 2019, but this was just out of intuition and gut feeling. And now I quite like this result because this is really now closing the gap between what we thought would be the reasonable thing to do and now what we can prove. So this is now really closing this theoretical gap, which I quite liked. Now, I said that I give you a circuit and I promise it's a good one. Either you can train these circuits, but there's a ton of alternatives how to define good parameters for these circuits in a very, very active area of research at the moment. There's some physically inspired parameter initializations. You can leverage a property called concentration or transfer of parameters, so you can use parameters that you train for one problem and apply them to a different one, and there's some theoretical argument why this often is good. You can do light-cone optimization. That means that you actually, since you look only at local observables, you can throw away parts of the circuit and many more. Tensor network simulations, different perturbation theory. So there's really a bunch of things. And this is very interesting because this training loop is quite a bottleneck. If you could take this out, this would push these quantum optimization algorithms to a completely new level. And this is something we are also working on. All right, we tested this for different cases. This is now a 40-qubit example. This is a max cut of a 3-regular graph. So it's not a difficult problem, but it's a good benchmarking problem for an algorithm. We chose a line of 40 qubits, and we compiled this problem then. And this is for different, that's between 500 and 1,000 CMOC gates that we had to apply here. And we classically determined the optimal parameters, because we could do some light-cone optimization. And then we run this on a device. And here you see these layer fidelities. So for p equal 1, so for 500 gates, it's like 10 to the minus 3. And for p equal 2, it's like 10 to the minus 6. So these are now the probabilities, not 10%, unfortunately. And we run both with 10 to the 5 and 10 to the 7 shots, respectively. What we wanted to see is we wanted to validate our theory. And what you see here is the objective values and the corresponding distribution probabilities that we sampled from the quantum computer. In blue, you have the expectation value from the hardware. In this dotted dash, you have the expectation value that the noise-free circuit would give you, and in this case it can achieve. This is the global optimal solution of the maximization problem, and the dotted line is the upper bound from the C-bar. Now we do the C-bar from the other side because it's maximization or minimization. And this matches very nicely, so it's a very nice validation of the theory. Then for the largest circuit, we did the same. Again, the upper bound is better. It's not better, it's larger than the noise-free expectation value. The discrepancy goes a little bit, it's a little bit larger, but that makes sense. And so we were very happy with that. Now, I mentioned before that QAOA for max cut on 3 regular graphs is actually not only a heuristic, it's an approximation with performance guarantees. And this is pretty cool because now we can recover this performance guarantee from the noise-free heuristic approximation and lift it to the noisy case. So by taking 1 over layer fidelity more samples, we know that the algorithm must achieve at least a, 68 or something % optimal solution. This is pretty cool because it's provable approximation on a noisy device.
That's still for max cut on 3 regular.
Yeah.
Okay.
Yeah. There's one caveat. The layer fidelity, of course, grows exponentially with the number of qubits. So it's usually, if we talk about approximations, we want them to run in polynomial time. But still, we have a performance guarantee. Okay, we also tried this on a 127 qubit device, not on a QO in this case, but on a cubic binary polynomial optimization. And this illustrated here, the single qubit terms are plus minus 1 depending on the color. The 2 qubit terms have a plus minus 1 weight depending on the color. And for each ellipse here we have a 3 qubit term or a cubic term with a plus minus 1 weight depending on the color of the ellipse. So it's a problem that natively fits on the hardware, so it's a very constructed problem. Here the layer fidelity for doing 1 round of QAOA is 10 to the minus 8. So here we didn't do more than 10 to the 8 shots because that would be a little bit too much. We just did 10 to the 5 shots for 1 to 5 QAOA rounds. And here you see the results. It's now a minimization problem. And since we don't have enough shots, we cannot take the C-bar here. But what we did is we turned it around. We still have the noise-free expectation values from tensor network simulations. And what we did is we fitted an alpha to the expectation value. And this is this kind of gives us an effective layer fidelity if you want. Because the layer fidelity is a little bit conservative. It counts also errors that you might not care about, like a phase error before a measurement is something that doesn't affect the measurement. And here we kind of get to some extent an effective layer fidelity. This is what you see here. And here you see the number of CMOC gates from 300 to 1,500, and you see it's from the effective layer fidelity is 46% down to 0.1%. So it's significantly higher than what the theory would say would be a 10 to the minus 36. So the theory is very nice, but it's people are using larger circuits, it's counting too many errors. And this also shows us that using the C-bar with significantly higher levels makes also sense as a good loss function. You lose this theoretical guarantee, but you still get a very good heuristic out of it. All right, let me conclude here. So I think the first point is on the complexity part. What is complexity theory good for in quantum optimization? I think it's very important to know what we aim for. You don't have to aim for a polynomial quantum algorithm that solves all NP-hard problems. This is very unlikely to happen. But it makes a lot of sense to come up with good approximations, with good heuristics, and so on. And particularly for heuristics, we need to try them. Classically, analog quantum, we really need to make use of this trial and error, and not only pen and paper research. And the two go hand in hand, of course, and one augments the other. And I think this is crucial, and we're currently building a set of benchmarking problems that we also want to publish that are difficult, not too big, that can help to track progress here. Then, in optimization, we often, most of the algorithms rely on sampling, not expectation values, and it's important to understand that this is much more difficult than expectation values. I think here, with this layer fidelity, we understood significantly more what this means and what to expect, and also how to possibly compensate for the noise. And for these Q&A algorithms, or type algorithms, I think, and we also see this in the research, in the papers, it's really crucial to move away from these variational loops and try to find problem-inspired ways to fix these parameters, because that just cuts down the runtime so significantly, and this would enable a whole new set of algorithms and suddenly also would be practical. And yeah, as I said, for all of this, it's crucial that we do this. We can talk about this, we can write about this, but we will not understand it until we do it and run the experiments. And just the last point, the error mitigation that we do for optimization is essentially just do more samples. We just quantify how many more samples. But of course, there could also be more advanced things like that. You can think about, I call it here lightweight error correction schemes for optimization, but you can have more noise robust encodings of your problems, leveraging symmetries. I think there's no limit to what we can think and try. And I think this can also be a very promising direction to scale quantum optimization algorithms, to maybe reduce the sampling overhead that's introduced by the layer fidelity, and look at larger problems. And with this, thank you very much for your attention.
Questions?
Thanks for the nice update. You're focusing on sort of classical optimization problems. I was wondering if you could comment on looking at particular classic optimization problems coming out of machine learning, which I suspect is a very hot topic for quantum researchers as well. Could you comment on how you look at that? Because you were looking at very classical optimization problems.
So I am looking at quantum optimization, classical optimization. Of course, we at IBM, we look at machine learning and quantum chemistry materials, so that we look at many examples here. For machine learning particularly, this is very interesting. There are a ton of proposals for quantum neural networks, for quantum reinforcement learning. Some are variational in such a way. Others are kind of using quantum linear algebra subroutines, for example. They suffer from different problems. And there's no clear answer where there might be an advantage. There are proofs. Actually, we heard about discrete logarithm. You can translate discrete logarithm into a learning problem, then you can construct a quantum kernel and plug this into a support vector machine, a classical support vector machine, and one can prove that this learning pipeline can solve this problem efficiently with one computer, but classically it's not solvable. So there are these proofs for the very constructed problems. For the other more, let's say, more variational, let's say you have one neural network that you plug into a larger neural network and you train this whole thing, there are indications that this might have higher capacity, that they might generalize better with smaller data, and that there are different proposals and tests that on a small scale have been proven interesting, but there's one big limitation to scaling them, and that's gradient computation is linearly expensive, so you can't backpropagate and get kind of a gradient for free. You have to look at every partial differential itself. Yeah. And backpropagation is one of the things that allows us to scale large classical like neural networks. And this is a thing that is very difficult on a quantum computer. So we have to rethink the models, we have to rethink the training algorithms.
Is that because of the sequential nature of Leibniz rule, essentially, that you have to kind of do one thing?
I think it's more about Born's rule, that the quantum state collapses after measurement. So there's a limited number of information you can extract. And from all we know so far,
So backpropagation is hard.
I mean, it's linear. Linear is not strictly speaking hard, but in this dimension we're talking about, linear is too much. And there are also no theorems that it's unlikely that we can do it more efficient. So we really need to find more or new ways of training, that new kind of models. There are hybrid models where you only use it as a non-linearity, but all the training happens on the classical side. So there are tons of proposals, but it's completely unclear.
In the interest of time, the next question should be done during the break. So, thank you very much. The next speakers are